We are the University of West Florida Marine Robotics team, part of the Department of Electrical and Computer Engineering in the Hal Marcus College of Science and Engineering.
Hi, my name is Remy. I'm a junior at the University of West Florida going for a dual major in computer and electrical engineering.
Hi, my name is Eric Labrat. I am a senior in the Electrical and Computer Engineering Department at the University of West Florida.
My name is Carly Billings. I graduated from UWF with a degree in environmental science in 2013, and I worked in informal science education for a few years before returning to UWF to study electrical engineering.
My name is Tati. I am a junior, majoring in electrical and computer engineering at the University of West Florida. I was a corpsman in the Navy for 6 years before I decided to pursue engineering.
I'm Charles Hostick. I'm retired from the United States Air Force after 22 years. I've come back to college to become an electrical engineer. I'm minoring in mathematics and excited to be part of this program. The goal of this project is to design, build, and program an autonomous surface vehicle, or ASV, to compete in the RoboBoat competition. Over the past 2 years, we have prepared hard to compete. We started with the Argo 2, a platform that quickly fell into disrepair.
At the start of our project, we used an existing boat. When we opened it up, there was a giant full-size computers and many components that we were not familiar with. And because this was our first exposure, we had to learn each component one at a time. We tested this boat on water and discovered that there was a leakage problem. We later found out that it was the motor bracket that was weirdly mounted and failed, which was the cause of the leak. The design of the old boat itself did not allow us to do some of the things that we wanted to do. So we eventually abandoned most of the parts and only ended up using the batteries in the Blue Robotics T200 motors. Through all of our efforts in testing of the boat, we ran into the same reasons why the previous group failed. And after extensive research, we developed a list of desired components for our project. We were pleased when the department approved our list in total, and they have continued to be supportive of our project. For that, we are thankful.
So we had to move from that to continue our testing. We went to a wagon. We tested a lot of individual components using the wagon. Unfortunately, it didn't have a drive system, so we quickly found ourselves needing an alternative. One day the team was actually looking for some other components that belonged to a previous boat team, and we found a tank by Super Droid Robots, and an idea was born. We re-engineered the tank to receive the boat equipment so that we could use that to continue our test and development to obtain autonomous operation. The tank actually matured into a very robust platform, allowing us to do a lot of testing. It actually did much better than our gazebo virtual testing because it was real world. We have actually had a successful autonomous test with the tank, albeit we have a lot of progress to make still. The biggest advantage of using the tank for test and development is the quick turnaround that we can make with deploying the tank. When we had Argo 2, the boat, we would spend an hour or more in preparing and getting to the pool and launching the boat. So the tank allowed us to be able to, when we were ready, we thought we had a program we wanted to test or a component we wanted to test, within minutes we were outside testing that component or that system or that software. Of course, there did come a point where we had to switch our attention back to the Argo 2. We needed to be in the water. It is indeed a boat competition, and the tank is not very buoyant.
One of the biggest issues with the Argo 2 is that there was no way for us to easily move our components to the tank for testing and back to the boat again. The tank was too valuable to us for testing purposes for us to abandon it, and buying every component twice just wasn't an option. Once this year's RoboBoat competition was canceled, we had plenty of time to pursue the creation of a new boat, which we have named the Nautilus. Whereas the Argo 2 was molded out of foam and fiberglass, leaving little to no room for design changes, the Nautilus is going to be built on individual pontoons in a way that lets us make changes if we need to. For example, we can remove a pontoon if the boat is too heavy. We can also adjust the angles that our thrusters are mounted at. And most importantly, the Nautilus is going to be built in a way that lets us move all of our components to the tank for testing and back to the boat again. All of our components are going to be mounted on top of an aluminum sheet which will fit on either the tank or our new boat. And being able to move all of our components back and forth means easy testing, whether we have access to the water or not.
A few unique things about our system design for either platform that we put this on. One of the things we switched to for power management and installation of much of our components was a DIN rail system, which we found was an excellent power management. It was a little bit more complicated to set up, but once you set it up, the power management is great. We use it for logic and the power, and it's just been a real pleasure that we haven't had to sit and chase problems with power and logic, and rather can focus on the task at hand of testing and development of an autonomous vehicle.
In designing our robot, we've discovered that complexity is an important issue to consider in design and strategy. Something we discovered early on is Murphy's Law, that if anything can go wrong, it will. Something to that note, we have a Xavier as our main computer on board. It's made by NVIDIA, but we discovered that it only had 2 serial ports built in, and we have a lot more devices that need serial port to communicate through the rest of the unit. We decided to implement a STM32, which is a lot like an Arduino. This is an Arduino here, this isn't the STM32, where it's a microcontroller that we can send information into, process it, and output it wherever we need it. We were going to use it to take in information from the GPS via a serial signal and compute it and send it up to the Xavier. We ran into a few issues because the STM32, while it is a more powerful board, was also more complex and harder to use. We had to write drivers to compute the GPS data we were receiving. And in the end was much more work than it could have been, because we discovered there was a board that added more serial ports via the PCIe slots on the Xavier, which once we had that, we were able to communicate directly into the Xavier, and it was able to run all the computations that it was taking in no problem. So we decided to scrap the STM32, take it off the unit completely. And that just goes to show, when you have something complex like that, it takes time away. It took us a couple months to get all that stuff working, where with the serial board we could have had it in a couple days.
Our overall strategy is to use RAWs to derive a globally referenced location and path plan, and cross-reference this with the information from our local sensors in order to determine where our obstacles are and the best way to move about them. To discuss the specific tasks in detail, the navigation channel and obstacle challenge are similar enough that we can group them into the same group of challenges. To navigate through these, we would use computer vision in order to detect where our buoys are and navigate around them, and place them on the global schemes so that we know where they are for future reference. The obstacle field and speed gate are very similar to these previous 2 challenges. However, they differ in the fact that we know ahead of time going into them the path that we intend to take around our obstacles. So then we just need to navigate to these challenges and execute our predetermined most efficient path. For some of the more complicated challenges, such as acoustic docking, we intended to use the hydrophone in combination with computer vision, and then combine that with our currently established global plan, which is externally referenced GPS, in order to navigate to this dock where we would execute our docking subroutines. Object delivery is more of a theoretical challenge for us. We intended to use an inertially stabilized arm, similar to how inertially stabilized camera mounts are done, in order to counterbalance out the chaotic motion of our boat. From here, we would attach a spring-loaded magazine in order to reduce our algorithms for this from a pick-and-place robotic arm to a simple place robotic arm that reloads between placements. From here, the only challenge left is the return to dock. Here we would leverage our generic globally referenced design in order to avoid driving through previous portions of the course that we've already navigated through, while still maintaining an efficient and direct line back to where our team is situated at the dock. Overall, our strategy relies on maintaining a robust awareness of our surroundings, as well as an awareness of how our local sensor input affects where we lay on a global scale.
The team would like to extend a special thanks to Dr. Kaboo, our department head who has provided us with tremendous support, as well as our mentors, Dr. Yusuf and Sam Russell. We'd also like to thank Scott Smith with Northwest Florida State College for his assistance and guidance with our welding requirements. Without all of you, our team's progress would not have been possible.